Right. So I've already done the magnetic field due to a long wire, and I actually did it numerically, and I did it analytically by forming an integral. So I want to do it again, and this time I'm going to use Ampere's law. So I wanted to do a bigger video about Ampere's law, but I didn't have all the programs built together. So I figured I might as well build the programs that I'm going to use first and then make the program. So this isn't the way I would teach it, okay? So I'm making this first, and if I'm making it, I might as well make a video, right? So what the heck? So let's go over not all of Ampere's law, because I'm going to make another video about that. I'm going to just use it. So this is Ampere's law. You see it right here. This says the closed integral. That's what that means. So that integral with a circle in it, the closed integral. It's a line integral of b dot dl. That in itself is kind of complicated. I'm going to show you that though. Is equal to mu naught times in, where in is the current that passes through that. So basically for Ampere's law, what you do is you pick a path to integrate b dot dl around, and then that's equal to mu naught, the constant, times the current that passes through the area that path makes. This is a lot like a two-dimensional version of Gauss's law, which I did make a video about. I made a video showing the flux, the electric flux through a cube, which was fun. But this is I'm gonna do this with Ampere's law. I'm gonna use this to find the magnetic field due to a long wire, which is that B equals mu naught over 4 pi 2I over R, and show that's how you get that. And then I'm going to do it numerically because I want to actually do the integral of b dot dl. And I have not set this up, so it might take a while, but I'm going to stick through it. I'm not going to quit unless it gets really bad. Okay, so let's do the analytical version. It's not so bad, and then we'll switch over. Okay, so suppose I have a long wire like this, and it carries a current I. And I want to find an expression for the magnetic field. So I know this, B dot dl equals mu naught In. The key to using Ampere's law is to recognize patterns in space and to utilize those patterns such that these integrals become trivial. Now when I do it numerically, they're not going to be trivial. Probably. Yeah. Okay, so if I look at this head on, just so I can see it, if I draw the wire right there and the current's coming out of the paper, then you can use your right-hand rule, thumb in the direction of the current, and your fingers show the direction of the magnetic field. And it makes these circular patterns. Now, you know, how do you get that? Well, technically you get that by doing this. B dB equals mu naught over 4 pi I dl cross r hat, let's say, over r squared. So this would be the vector r. If you want to find the magnetic field right here, this would be the vector r. I dl is a part of the wire coming out, and you take the cross product, and then you can do that. And this gives you the direction. And I've done that in another video, and I'll try to remember to include it down below. But if I know the pattern of field in space, then I can intelligently pick a path that will make this whole thing easy. So let's say that I pick, and this is not a real path, I'm just picking a path. What if I pick this path? A circle of radius r. If I pick a circle of radius r, then I can do this integral of b dot dl very easily. Because if I take this point, I know that B is that way, but I know also that dl is that way. So everywhere that I have on the circle, b and dl are in the same direction. And if b and dl are in the same direction, then I can write the vector b dot dl is going to be equal to the magnitude of b times the magnitude of dl times the cosine of theta. That's the definition of dot product, but theta is 0. So the cosine of 0 is 1, so this is just going to be b dl. Now, I still have to add up all the pieces around the path, but you'll note that if this is circular, and I assume that the magnitude of the magnetic field depends on the value of r, then all these have the same magnitude. So b is constant along this integral, and I can pull it out of the loop. So I get the integral of b dot dl vector equals b times the integral of dl. And now I don't even need to do the integral, right? If I want to integrate the path along the circle and add up the length of the path, that's just the circumference of the circle. So this is just going to be b times 2 pi r. And that's equal to mu naught times I n. So what's I n? I is the electric current that passes through this area. Well, I'll only have that one wire I passing through there. So that's just going to be I. So I get b 2 pi r equals mu naught I. Now let's solve for b, and I get b equals mu naught I over 2 pi r. Now, since mu naught over 4 pi is equal to 10 to the negative 7th Tesla meters squared per amp, Coulomb meters per second, I think that's right. Then it's nicer to write this as mu naught over 4 pi. So if I multiply this by 2 over 2, I get mu naught over 4 pi 2I over r. And that's the magnitude of the magnetic field due to wire. It's not the direction, because I already assumed the direction in order to get that. And that's what's kind of tricky about, kind of disingenuous about Ampere's law. I mean, it's very useful. Now, let me say one more thing. It's actually wrong. That's not the complete Ampere's law, and we'll get to the complete Ampere's law later. But that's just only a special version of Ampere's law. Just letting you know. I don't want you to catch me on that. Okay, so there we have the magnetic field due to a long wire. Now, let's do this in Python. Okay, so in Python, what we're going to do is this. Here's my long wire, which is not going to be infinitely long because it's Python. And I'm going to break it into pieces. N pieces. N equals, let's say, 10. And this has a length of L. And then what I'm going to do is say I'm going to start down here at, let's say, wherever I want. L start. It's going to be of some vector location. 0, 0, 0, whatever you want. It doesn't really matter. And then I'm going to find the current and the dl for each piece. So each piece is going to be, I'm going to draw it as a sphere, but it's going to have a current of I. It's going to have the dl vector of this. dl vector is going to be equal to, let's say it's in the y direction, 0, 1, 0. But then dl also has to have a length. That's a vector. And the length of this is going to be the total length divided by n. So now that when I integrate and add up the length of all these pieces, I will get n. So, but now with this, I can actually do some stuff. Number one, I can calculate the magnetic field anywhere I want. Say right there. So to do that, I'm going to take my, this is RO, my observation location. Here's my origin. So that's RO right there. This is the vector R, and then I need the vector RP for the piece. So R is going to be the final RO minus R piece. So I can find that vector R. And then I can say the magnetic field at that location, dB, is going to be mu naught over 4 pi I dl cross R hat over R squared. Actually, I always do it this way. I dl cross R over R cubed. So that's the magnitude of R, and that's R. And cross product is built into Python, and I can find that piece. And then I just go to the next piece, the next piece, the next piece. So my number one step is to build this. My number two, so 1, build wire. 2, I'm going to make a function B of RO. So this will calculate the magnetic field at any particular location. And then number 3, I can pick a path, a circular path, and I can start, and I can calculate the magnetic field. Once I calculate the magnetic field, I can calculate B dot dl and add that up around the path. And then I don't really even know what I'm doing right now. I'm winging this as I go on, so let's just jump over to Python and see how much damage we can do. Okay. You with me so far? Okay, let's switch to the computer. So here we are with Python. I'm using GlowScript v Python in Trinket. Let's go ahead and save it. Ampere's law 1. I don't know why it's 1. It's number 1. Okay, and the next thing, my mu naught over 4 pi, I'm just going to call Km. I did that before. Km equals 1 times 10 to the negative 7th. I don't know if that really matters. Now, I did have a problem in my previous video with GlowScript 3.1, so if there's a problem, remind me. That's what the problem is. Okay, next thing, I need to pick the length of my wire. Let's say L equals half a meter, and I is 1.2. Just picking something. So I want to build that wire. Yeah, let's do that. So n equals, let's start with n equals 10, and I need the starting location. So L start, let's say it's equal to vector 0, negative L over 2, plus So I want to, if I have n as large, this would be fine, and I want to just do that. But if I want the actual center of that piece, then I need to move up by half of, let's see, so let's say DLL is going to be L divided by n. So I need to move up half of that distance. So plus DLL divided by 2, right? So if I'm all the way down to the bottom of the wire and move up a little bit to get to the middle of that piece, that would just make me feel a little bit better. 0. That's my starting location. Okay, I think we're ready. So also I'm going to say this, wire equals a list. I'm going to add spheres to this list. And that way when I go to calculate stuff, I can just go back and look at the things in the list. I'll include a link to my list down below if I remember. And if I don't remember, then I will have forgotten. I wouldn't even know that I didn't remember, right? So that's an easy problem. So there's my wire. So now I'm going to say while, n equals 0, while n is less than n, and let's just test this, right? Print n, just to see how this works. N equals n plus 1, and let's save that, and that should go 0 to 9. There we go. So it's working. That's a good little test. That's where we start with low numbers of n. I do need that. I don't need this. Okay, so now the first thing I'm going to do is say the location of the wire, RW, is going to be equal to L start, which is a vector, plus, let's call this, let's say DL. I see I'm going to have more than one DL. That's what I'm kind of not happy about. I'm going to have like 3 DLs. How about this? DL equals, I want my wire in the y direction. So DL is going to be equal to the vector, so L over n times the vector 0, 1, 0. Yeah. But now this DLL is, and so now this DLL, I can just say this is going to be, let's just say mag. This is nasty. I don't really need to do it that way, but I think that's okay. I could just say DLL over 2. That's really what I should do. I should say this plus DL over 2. Yeah, let's do that. Okay, so now my piece is going to be the starting location plus n times DL. Right? So if my first one, n is 0, so my start is at the start. The next one will be at, I'll move up a length DL. Okay, so now I need to make a sphere. So let's add it to the list. So let's say wire equals wire plus a sphere. The position is going to be RW. The radius is going to be equal to the radius is going to be equal to So it's a 5, so let's say it's centimeters, 0.01. And let's give it this too. Let's say DL equals DL. I don't like that. Okay, let's go back up here and say DLL. But in this case, what I'm doing is I'm actually adding a parameter to each sphere called DL. And then I can reference it later. And they're all the same, so it doesn't really matter, but I think it's just a good habit. So this is DLL. Okay, and then that's that. So let's see what happens. Can't find DL. DLL. Okay, 10, that looks good. 10 spheres. Everything looks fine, so we could change that to 100. That's what we're going to have it. I have 100 things on that list. Now it actually looks like a wire. Okay, so I have my wire, I have my current. Check. The next is to define a function to calculate the magnetic field at some particular location. Okay, so let's say def b r o. So I'm going to pass to it the location of where I want the magnetic field. I'm going to return the vector at that place. Okay, so here's the thing what I'm going to do. I'm going to start with this. B equals, B temp equals 0. No, vector 0, 0, 0. Because I'm going to calculate the magnetic field due to each piece and add it to that. So I need to know that the starting piece is 0. Okay, so now let's do this. For RP in wire. So since wire is a list, I can go through each element of the list. And in each element of the list, the first thing I can do is calculate R. So R equals RO minus RP, just like I said. Okay. Now I can calculate DB. DB equals mu naught over 4 pi, which I'm calling Km, times the cross product of, or times, well, I could do it, I times RP dot L dot DL, right? That is my DL vector. Yeah. And with R. So it's I DL cross R. And I'm going to divide that by the magnitude of R cubed. Now I'm going to add that to my total. So BT equals BT plus DB, and that's it. And then I'm going to return BT. So let's just see if this works. Let's say B theory equals Km times 2 times I. Let's say R temp equals 0.01, kind of close to the wire. Km equals 2 times I. Okay, where does it go? It's mind blank. 2I over R, right? 2 over R temp. That's the theoretical, and let's print that. Let's just to make sure it works, and we'll leave off the units even. B theory. And now let's print. And I want it on the x-axis. So let's say print. Don't even do it. Let's say B calc equals B vector 0.01. I'll say R temp 0, 0. And let's see if that works. It should be close to the same value. If not, it won't be exact. Let's save that and run it. Okay, got an error. Cannot subtract RP. Oh, so this is RP is the actual sphere, so I need RP.POS. Yeah. Okay, that worked. Okay. Those two numbers are about the same. I'm pretty happy. Are you happy? We can even put a arrow there. So I could say, let's just put arrow. I need B scale. B scale equals, let's say 10 to the negative, 10 to the 4th. Let's say, I was using 2 to the 4th before, so let's try that, or 3. So now I can say arrow position equals vector R0, R temp 0, 0. Axis equals b scale times, I should have had that as a actual value. I got to rerun the function just because I'm a lazy person. And let's make it yellow. That's wrong. I'm glad I did that. Well, that says B calc is in the Z direction. B calc is in the Z direction, which is in and out of the paper. And that's the screen. That's correct. But the arrow's wrong. Axis is B scale. B scale times. Oh, you know what? Maybe it's just so big. No? Let's make that a little bit smaller. Oh, position is R temp. That's right. Oh, it is in the board, but just in the wrong location. Maybe it's just so close. I think it's just so close. That's the thing. Let's change this to point. Oh, that's right. It's just too close. So let's change this to R temp to 5. Change all these to 5. R temp. That's fine. Okay, now that's good. It was working. It was just too close. So let's make B scale back to 2. Okay, so I have so far made a wire as a list, and I've made a function so I can calculate the magnetic field anywhere. Next, I'm going to make a path. So I want to make a path around that thing. So let's do that. And I'm going to make the path as a list too. Let's see how that works. I'm going to make it a list of spheres. So let's make our path. Okay, so let's call it path. Path equals an empty list. And now I need our path. What's the radius of my circle going to be? Let's say it's going to be equal to, drawing a blank here. So how about 0.1? Nah, 0, yeah, because that's 5 centimeters. That's kind of small. So let's make it twice that. Okay. Now I need in path, right? How many pieces am I going to break it into? I'm going to start off with 10. I like 10. Now I'm going to say theta equals theta start equals 0. D theta start equals 2 times pi divided by n p. So what I'm going to do is I want to go all the way around that circle. And so I'm going to break it into angular pieces. And so that's going to make it easier to calculate the location of each thing. And I did this before and in my program for the magnetic field due to a loop. Okay, so now I can say while, let's say theta equals 0, while theta less than 2 times pi, do the following. So all the way around the circle. First step is to find the location of the piece. So let's say RPP for, I don't want to use the same variable. It's going to be our path times, and I should draw a picture here, but let's do that. I say I should draw a picture, then draw a picture. I mean, that's not hard. So let me switch over here to the paper. So I want my circle, this is the y direction. So I want this in the x z plane, right? Because my wire's in the y plane. So this is my r path, and this is my angle theta. So I want to make a circle around like that. So the x coordinate is going to be r path times cosine theta. The y coordinate is 0. The z coordinate is r r path sine theta. And then I'm going to increase my theta by d theta, which I call d theta start. And then I'll go to the next one, and the next one, and I'll get all my pieces. Now, the other thing I'm going to have to do is get dl for this too. So if I take this as rpp, that's my path piece, okay? And this is the vector y hat. And I want to find this is my direction dl. So if I take this y hat and that r, and I take the cross product, right, I get that vector. So dl is going to be the magnitude, see, y hat cross the rpp hat, all that times 2 pi r path over n. Right, because I need this is the total length. I need to divide it by those pieces. Okay, so let's just try that. I'm already at 26 minutes. No way I'm going to finish this under 30 minutes. Okay, but that's okay. No one's in a rush, right? Are you in a rush? Where do you have to go? So what was I doing? Okay, so r path times vector cosine theta 0 sine theta. Now let's add a thing to there. So let's say path equals path plus, I'm going to draw these as spheres, which is kind of silly, but I don't really care. So I'm adding a sphere. Its position is rpp. Its radius is going to be 0.0. How big? Let's try 0.5. And I'm going to leave it as clear. Now I'm also going to have a dl, right? So dl is going to be the cross product of the vector y hat. So it's going to be vector 0, 1, 0 and rpp hat. So norm rpp. All that times 2 times pi times r path divided by np. Now down here, I'm going to increase theta. Theta equals theta plus d theta start, which is kind of weird, but that's fine. And let's see if that does it. Kind of scared. Oh, looks like it worked. Okay, let's get rid of that arrow down there because we don't need that. I do want to keep b scale. So let's just get rid of this and get rid of that. Okay, now one other thing. Let's go through and just put arrows on there. And I'm trying to think if well, I think it's going to work. I did that before and I think it worked. So I could change this to 100. And there's my loop that along which I'm going to calculate my path. Okay, we're making progress here. Okay, so next I'm going to go through that path and calculate b, and then calculate b dot dl, and then add it all up. Okay, so let's call this. Let's say this. What are we going to call the loop? Let's call it what should I call my sum? Let's call it sum. B sum equals 0 because I need to calculate that. So now I will go for RTT in path. So this will go through each element in the path and do whatever I want to do. Okay. So the first thing I'm going to do is to calculate the temp magnetic field, RB temp equals B RTT.POS. So I'm going to pass the position of that path to my function to calculate the magnetic field, and then I'm going to return a vector value of the magnetic field, and then call that B temp. Now with that, I can calculate, let's call this temp, let's just call this dB sum. It's going to be B, the cross product, so no, it's dot. the dot product of B temp and I, no wait, not I, B dot DL. So just do DL. So I say B temp and RTT dot DL. I think that's right. And then I go down here and I say B sum equals B sum plus DB sum. And that should do it. Okay, so now I'm going to say let's print. So if once I calculate that and I multiply by, divide by mu naught. So I need to divide by, actually, let's switch. I want to get in terms of this. So I'm going to say the integral b dot dl is mu naught in. So I calculate that and divide by mu naught, and mu naught over 4 pi is 10 to the negative 7th. So mu naught is 4 pi times 10 to the negative 7th. So I'm going to take this, divide by mu naught, and I should get the current. And let's see if we do. So let's call this mu naught is 4 times, let's say pi, times 4 times 10 to the negative 7th. So print B sum mu naught. Let's just say iCalc equals, and it's going to be B sum times mu naught. Now, if this works, I'm going to be really excited because I just things don't work. And let's print just for print I real equals I. And I'll leave off the units. Okay, you ready? Save. iCalc is 1.7 times 10 to the negative 12. That's not right. What if I change this to 10? Still the same thing. Okay, so what did we do wrong? I want to check that my path is actually 2 pi r, right? So let's just do this. For RTT in path, let's say up here, circ equals 0. That's the circumference. So I'm just going to add up the magnitude of dl for each piece, and I should get 2 pi r. So circ equals circ plus mag rtt dot dl. And that's it. And then I'm going to print circ, and I'm going to print 2 times pi times r path. Those should be the same. Okay, so that's good. What about DL? Maybe that's wrong. Okay, so let's do this. Change this to 10. And so those still work. And let's go ahead and, I don't need this. But let's just go through each element in the path and draw an arrow. So I'm going to put an arrow. The position is going to be equal to rtt.pos. The axis is going to be equal to rtt.dl. That works. Wow. Okay. So up here, B sum dot rtt.dl, b.dl, r temp. I've only got 10. Let's just print out these B's. Let's put an arrow for B. So arrow position equals rtt.pos, axis equals B scale times B temp. So at least we can see what that looks like. I'll get rid of these. I don't want that on there. Okay. Huh. Mu naught equals 4 pi times 10 to the negative 7th. That's right. I calc is B sum divided by mu naught. What the heck? What an idiot. Okay. At least it's working. Okay, so let's change this back up to 100. There we go. It's not perfect. It's good enough for me. I mean, because there's two things, right? I have two discrete pieces. Oh, my wire is only 100, only 10. Let's change this to 100. Okay, it's still 1.2. I'm surprised it's off. But I think part of the problem is I don't have an infinitely long wire, and so my approximation isn't perfect as I get further and further away. But I'm happy enough, right? I guess let's do this. Let's make L. What if I just make L equal to 1? So it's twice as long. Yeah, it's closer. Okay, so I think that's good. I didn't want to make the ring too small because you couldn't see it. Okay, so now, actually what I could do, let's do this just for fun. For RTT and path, so I calculate the b.dl. I need a scale, right? I need what is the value of BL? So, because I want to make I was going to make them colored, right? The ball is colored red if it's a positive BDL, blue if it's negative. So I could just do positive or negative, and not this value. Let's just do that. Okay, so let's say if dB sum greater than 0, then RTT.color equals color.red. Else RTT.color equals color.blue. So these should all be red. And they are, but the thing, well, I have two on there. There's two. Did I draw it twice? Let's see. I have two spheres. I think it should just change the color. Why didn't it change the color? Okay, well, I'm not going to worry about that because there's something weird going on. I want to do the following. What if I move my wire over here? If it's over here, right? I could actually plot b.dl. That's what I should really do, make a graph. I'm not going to do that right now. I'm gonna move this over here. So now I will not have a path, a magnetic field current passing through my loop. So let's put my wire, let's just move the wire. I can do that, right? I can put this at negative 0.2. That's all I did, was move the starting location over. There we have that. What's that blue thing? Oh, it's negative. I did do it. Huh. Why didn't it do it before? Oh, there's still that. Oh, and those are arrows. I'm drawing some arrows somewhere. Where am I drawing arrows? There. That's what that is. Okay. So it did work. So now you see the calculated I, or the B divided by mu naught, is close to 0. So right here, this, if I'm going around the loop this way, this part of the loop, I'm pretty happy with this, right? This part of the loop, B and DL are kind of in the same direction, so you have a positive B.dl. But on this side, you have a negative B.dl. And since the magnetic field is stronger over here, B is stronger. So that once I do B.dl for all these negative pieces and add it to all these positive pieces, I get 0. Isn't that cool? So Ampere's law still works. It's just not useful. It's just not useful. Let's do this. What if I put it still in the loop, but not in the middle loop? So if I put this at negative 0.03, So now it's off-centered. And you see, this still works. I get it, as long as it's passing through that thing, then the magnetic B.dl is still going to add up to the same as the total current times mu naught. So there you go. That's a numerical version of the Ampere's law. And I do want to make a plot of B.dl. I just don't want to do it right now. I don't normally make 40-minute long videos, but when it takes 40 minutes, it takes 40 minutes, and I did it. I'm kind of happy. I hope you're happy too. So I'm going to use this. I think I'd like to do this for a couple other cases and maybe improve this a little bit. I'll give you the code. You can improve it if you want, as long as it makes you happy. So I'll try to include all the things that you need for this. So that's that.